Lami's equations for a thick cylinder, both for radial pressure as well as hoop stress. So this Px is the radial pressure. So at a distance x from the center of the cylinder. So the minimum value of x is Ri, internal radius, and the maximum value is Ro, outer radius. Okay, so x can vary from Ri to Ro. So this is the cylinder part. Thickness of the cylinder is T. So if the thickness is more than 1/10 of the internal diameter, then it is called as a thick cylinder. That is the definition. So Px is the radial pressure, which is compressive in nature, whereas sigma x is the hoop stress, which is tensile in nature. Okay. So to find those two things, we are using that Lami's equations, which we had derived like this. Px is b by x square minus a. Sigma x is b by x square plus a. So from these two equations, we can observe that sigma x is always greater than Px. And nature-wise, Px is compressive, sigma x is tensile. And this A and B, they are calculated using the boundary conditions. So using the boundary conditions means at x is equal to Ri, Px is equal to Pi, and at x is equal to Ro, Px is equal to Po. They are the boundary conditions. By substituting those boundary conditions in those Lami's equations and solving, we got the values of A and B. After substituting the values of A and B, you can get the expressions for the radial pressure PR and hoop stress sigma R at any distance R from the center of the cylinder. Just by knowing the value of R, you can find the values of PR and sigma R, and later on you can sketch the diagram, and the difference between this sigma x and px is always 2a, and the variation is a parabolic variation. Now we can have some problems, in which case they will ask you to sketch the stress distribution, radial pressure as well as hoop stress. Okay, so stress distribution across the section they may ask. In some books, they call this radial pressure as radial stress also. So don't worry. So they can call it as radial stress. Only thing is pressure is an external effect, stress is an internal effect. So numerically they will be equal. So numerically those values will be equal. So whether it is stress or pressure, you need not worry about that. So the units are same, Newton per mm square. Now let us take problems on that. A pipe of 300 mm internal diameter and 100 mm thickness contains a fluid at a pressure of 80 Newton per mm square. Find the maximum and minimum hoop stresses across the section. Also sketch the radial pressure and the hoop stress distribution across the section. Section means across the thickness. So here thickness he has given 100 mm, internal diameter 300 mm. So therefore the radius, internal radius becomes 150. See, you should be very careful here. In some problems they may give diameter, some problems they may give radius. So you should be very careful. So here diameter is given. When diameter is given, radius is diameter divided by 2. So he has given 300 mm as the internal diameter. Therefore internal radius Ri is half of this. 300 divided by 2, which is 150 mm. And outer radius will be naturally this internal radius plus thickness. So please note that Ro is Ri plus T. So from the diagram, you can see that. So it is 150 plus 100. 100 mm is the thickness. So it becomes 250. So Ri is 150 mm. Ro is 250 mm. And in this case, he has given only internal pressure. So internal pressure only is given. So Pi value is given as 80 Newton per mm square. The external pressure is 0 here. He has not given any external pressure. If they give external pressure, then only you have to take that value. Otherwise, you can keep it as 0. Okay. So in this problem, PO is 0. Pi is 80 Newton per mm square. Thickness of the pipe is 100 mm. Now, first step, we have to find out the constants A and B. So that is very important. So A and B constants we have to find out. So he has given, we know the values of the pressure. First equation, Lami's equation, you can use here. So using the Lami's equation, Px is equal to b by x square minus a. This is the equation for the radial pressure. We will use this equation because we know the value of P here. So at the inner radius is 150 mm. So that at x is equal to 150 mm, Ri is equal to 150 mm, Px value is 80 Newton per mm square. You substitute that here. So 80 is equal to B by x is now 150 mm. So x is the distance from the center of the cylinder, that is the radial distance. So you have to take x is equal to Ri. When x is equal to Ri, P is equal to 80. Okay, Px is equal to 80. Please note that. So 80 is equal to B by 150. Are you seeing the screen? Are you seeing the screen?
No, sir.
Any one of you answer, please.
No, sir.
Now, can you see the screen?
Yes, sir.
There was some internet problem. Yeah. See, once you get the values of A and B, you just substitute in that equation Px is equal to B by x square minus A. So this is what you will get. Then what you have to do is, he has asked you to calculate the minimum and maximum values. So I have told you that the maximum value occurs at the inner surface of the cylinder and the minimum value occurs at the outer surface of the cylinder. So the minimum values, you can just go on substituting the values for x here. So what happens here, if you want, so starting from 150 to 250, okay? So you have to get the values. So of course in this problem he has done for 3 values of x. Are you seeing the screen? Is the screen visible?
Yes, sir.
Okay. So he has calculated the px values and sigma x values for 3 values of x. So at x is equal to 150, that is the inner radius, you have to put x is equal to 150 here. Okay, so if you put 150 here, you will get naturally 80. You know that the given value of px at x is equal to 150 at the inner surface is 80. So you will get 80 only. If you put x is equal to 150 here, and if you simplify, you will get 80. Next, another value he has taken at x is equal to 200 mm. Put x is equal to 200 mm. That is at the middle of the thickness. So you have 25.31. Next, at x is equal to 250. 250 means at the outer radius. You are going to get, if you put x is equal to 250 here, you will get px value as 0. So the variation of the radial pressure, that is px, it is plotted like this. So in the diagram, it is plotted like this. See, this is the inner radius, this is the outer radius, this is the thickness, 150. This is center of the cylinder. So this is only a portion is shown here. 150 mm is the internal radius, 250 mm is the outer radius. So at 150 mm, the value of px is 80. At 200 mm, the value of px is 25.31 MPa or Newton per mm square. And at x is equal to 250 mm, its value is 0. And you have to join these points by a parabola. Please note that this is the radial pressure distribution. It is a parabola. Brackets you can write compressive. It is not written here. You can write compressive there. So radial pressure is always compressive. Next, if you want the value of hoop stress formula is sigma x is equal to p by x square plus a. Okay. So p by x square plus a. So maximum hoop stress naturally occurs at the inner surface of the cylinder, that is at x is equal to 150 mm. So which is just substituting this value, x is equal to 150, b and a always you know, all the values you know. So just substitute, you will get 170 Newton per mm square. So sigma x value, hoop stress value at the inner radius is 170. Next, same at x is equal to 200 mm, you substitute in that formula b by x square plus a. So x is 200 here, you will get 115.31. You can just see that it is reducing. And the minimum hoop stress occurs at the outer radius. So 250, x is equal to 250 mm. So b by x square plus 45, it is 90. So it varies from, you can see here, it is shown here. Hoop stress is plotted here. At the inner surface, it is 170. At 200 mm, it is 115.31. At the outer surface, it is 90. Join this by a parabola. Once again, a smooth curve, parabola. So this represents the hoop stress, which is tensile in nature. You can write in brackets, tensile. So this is the distribution of radial pressure as well as the hoop stress along the thickness. So this is the sketch. So sketch the variation of hoop stress and radial pressure along the thickness of the cylinder or along the section of the cylinder. If they ask, you have to find the values at some points. So mainly you need at the inner radius, at the outer radius, and in between 1 or 2 values you can find out. Just by giving the values of x, you can substitute and simplify. You will get, only thing is it will be decreasing in nature and it is parabolic, and radial pressure you will get compressive, hoop stress you will get tensile. Okay, so this is how we have to, you can also find at 4 values also. So what you can do is at 150 mm, then at 175 mm, then 200, then 225, then 250. So you can divide this into 3 or 4 divisions. So then you can find at those sections what are the values of px and sigma x, then join all them by a smooth parabola. So this is the distribution. So that means first we have to find out the constants a and b by using the boundary conditions. So boundary conditions are at the inner radius and at the outer radius, you will be knowing the pressure values. So at r is equal to Ri, Px is equal to Pi. At r is equal to Ro, Px is equal to Po. If there is no external pressure given, Po should be taken as 0, which is there in this problem. If they give the value, then you have to take that value, solve the two equations to find out the unknowns a and b. Once you know the values of a and b, substitute back those values in the Lami's equations to get the expressions for px and sigma x. So once you get the values of px and sigma x by knowing a and b and in terms of x, go on giving the values of x from minimum to maximum in intervals and find out the values and then sketch the diagram. Please note, radial pressure is compressive in nature, hoop stress is tensile in nature. That is why they are plotted on opposite sides. So this is the datum. With respect to that datum, you have to plot. It is not to scale, just you have to write the values, join them by a smooth parabolic curve. So this is one type of problem. Second type of problem is, see, calculate the thickness of metal necessary for a steel cylindrical shell of internal diameter 120 mm to withstand an internal pressure of 45 Newton per mm square if the maximum permissible tensile stress in the section is 120 Newton per mm square. See, this is how they will ask. So here in this problem, he has given the maximum permissible tensile stress. So here, please note that sigma x is tensile, hoop stress is tensile, and the maximum hoop stress occurs at the inner radius. That also I have told. That means he has given the hoop stress value here, because maximum tensile stress is the maximum hoop stress which occurs at the inner radius. So that means what you have to do here is at this point, inner radius point, you have to take the hoop stress value as 120. And Pi is given here, internal pressure 45 Newton per mm square. T is unknown here. So internal diameter is given 120 mm. So internal radius becomes 60 mm, half of this. So internal diameter 120, internal pressure 45, maximum permissible stress 120. See, this is the data given. Now using the relation, so same Lami's equation we are using, Px is equal to b by x square minus a. You substitute the boundary conditions. So he has given internal pressure as 45. So at the internal pressure means it is R is equal to Ri. R is equal to Ri. So Ri is 60 here. So internal diameter is 120. So therefore di is 120. Ri will be 120 by 2, 60. So put x is equal to 60 and he has given the pressure as 45. So 45 is equal to b by 60 square minus a. And the second condition, you cannot use the external pressure. PO is not known here and you don't know RO also. RO is also not known because thickness is unknown here. Your Ri plus T is RO. So we cannot use the same equation for the second boundary condition. Second boundary condition is, since he has given the maximum permissible tensile stress value, which is nothing but your maximum hoop stress value, which occurs at once again the inner surface of the cylinder. So what you can say, sigma x equation we have to use. Sigma x is b by x square plus a. Instead of minus, it is plus here. Hoop stress equation we have to use. And we know that hoop stress is maximum at the inner radius. That is x is equal to 60 here. Okay. Or r is equal to 60. So 60 square will come here. Maximum value is 120. So the other equation becomes now 120 is equal to b by 60 square plus a. Now we have to solve these two equations. Once again, two equations are there, two unknowns. So by subtracting one equation from the other, A will get cancelled. You can get the value of B. So it has been done here. See here, they have solving equations 1 and 2. A and B values are obtained. So solution is done in the same manner as that of the previous problem. Now we don't know the thickness value. We have to find the thickness value. Once you find the unknowns A and B, let us take R naught as the outer radius of the cylinder. Then once again apply the Lami's equation. Px is equal to B by x square minus A. He has not given any external pressure here. P naught is 0 here. So therefore, at R is equal to R naught, at X is equal to R naught, so Px will be 0 because he has not given any external pressure value. So 0 is equal to B value you substitute. R naught you don't know, just put it as R naught square minus A value you substitute. Solve for R naught. From this equation you will get R naught. Then we know that thickness is given by R naught minus Ri. Outer radius minus inner radius. You are getting 29 mm as the thickness of the cylinder. So it is very important. Okay. You can check whether it is thick cylinder or thin cylinder. So thickness should be greater than 1/10 of the internal diameter. Okay. So internal diameter here is he has given internal diameter as 120 mm. So 120 divided by 10 is 12. So thickness is 29. So 29 is greater than 12. So therefore it is a thick cylinder. So thickness should be greater than 1/10th of internal diameter. Then it's a thick cylinder. Whereas in thin cylinder, that ratio will be less than that. So, okay. So this is how, so depending on the data, we have to use the boundary condition. So boundary condition means those two equations only, Lami's equations only, one for radial pressure, another one for hoop stress. So radial pressure is compressive in nature, hoop stress is tensile in nature. Only difference is B by x square plus A for sigma x, B by x square minus A for Px. So depending on the data in the problem, we have to use the respective formula. Okay. So when they give maximum permissible tensile stress value, can you see now? Can you see the screen now? Students?
Yes, sir.
Some problem is there with the net. That's why it is going and coming. Huh? Anyway, so same type of problem. See here, Lami's equation, Px is equal to B by x square minus A. We are using the same equation. So P is 9. It is given at the inner, this thing. X is 250 we have to take. At the inner radius, x is equal to Ri means x is equal to 250. So that is one equation. Another equation, same thing. He has given maximum stress, allowable stress. Allowable stress means maximum stress. Is faulty means sigma x is equal to b by x square plus a. That we have to take. So faulty is equal to b by x square plus a. So once you substitute in this, once again you have to solve these two equations to get the values of a and b, and finally substitute back. Let R naught be the outer radius, same type of earlier problem. Let R naught be the radius of the outer radius of the cylinder. So you, after getting the a and b values, you use once again that radial pressure equation, and we know that there is no external pressure given in the problem. So at x is equal to R naught, Px is 0 here. So you substitute in this once again Lami's equation and get the value of outer radius. Outer radius minus inner radius gives the thickness 64.31 millimeter. Suppose if they give any external pressure P0 value, that value you have to take here. Okay. If they give 10 Newton per mm square or 20 Newton per mm square, some value, external pressure value, that value you have to take here. When x is equal to R naught, Px becomes P naught. But here he has not given that. They may give some value. If they give that value you have to substitute here and procedure remains same. So what I wanted to tell you is from these things, so once again I will just revise you from the beginning. Thick cylinders, in the case of thick cylinders, you will be having, as usual, radial pressure you will be having, hoop stress you will be having. Radial pressure will act along the radius direction. So hoop stress acts in the circumferential direction. One more stress is there called longitudinal stress, which acts along the length of the cylinder, which is taken as a constant. Okay, please note that sigma z, in this he has used it as sigma z along the length. So that is taken as a constant. And once longitudinal stress is constant, longitudinal strain also becomes constant. So using that concept, that Lami's equations have been derived. So it has been derived, equations have been derived for both Px and sigma x. Px is the radial pressure, sigma x is the hoop stress. Px is compressive in nature, sigma x is tensile in nature. So these two are the Lami's equations in terms of A and B. So derivation. So these are the Lami's equations. Once you get the values of A and B using boundary conditions means the values of Px and sigma x at the inner and not sigma x, Px, the value of Px at the inner and outer radius. We know that at x is equal to Ri, you have Px is equal to Pi, and at x is equal to Ro, you have Px is equal to Po. If Po value is not given, you take it as 0. So this is general equation which holds good for both internal as well as external pressures. Once the boundary conditions are known, so you can just plot. Once you get the values of A and B, you can sketch the variation of both radial pressure as well as the hoop stress along the thickness or along the section like this. Please note that this radial pressure is compressive in nature, hoop stress is tensile in nature. That's why they have plotted on opposite sides of this line, and they are parabolic in nature, because P, you can see that both Px and sigma x, they vary inversely as x square, b by x square minus a, b by x square plus a. That means x square term is there, that is why it is parabolic. So both of them, they vary parabolically. And another thing is, maximum values of both Px and sigma x, they occur at the inner radius, and minimum value occurs at the outer radius. That means it goes on decreasing. Stress value goes on decreasing, which is not there in case of thin cylinder. In the case of thin cylinder, this stress we are going to take same. Its stress becomes constant from this end to this end because the thickness is very small. Here the thickness is more than 1/10 of the internal diameter. So that is why there will be variation of radial pressure as well as hoop stress. So radial pressure and hoop stress, they act at right angles to each other. Please note that one in radial direction, another one in circumferential direction. So radius and circumference. Circumference means tangent. tangential direction. You can call it as tangential direction. So radius and tangent, they are at right angles to each other. So that is why they will be mutually perpendicular. Nature-wise, radial pressure is compressive, hoop stress is tensile in nature. So that is one type of problem. Sketch of the radial pressure as well as the uh, hoop stress. Another type of problem is finding the thickness of the cylinder given the maximum or the allowable stress value of the material of the cylinder. In that case, the boundary conditions will be one condition you can use first radial pressure equation of Lami's equation. Another condition you have to use the hoop stress condition of Lami's equation. So those two conditions, because we know that this hoop stress is the maximum value or the allowable stress value. So which occurs at the inner radius of the cylinder. So those two have become the boundary conditions. So if you solve them, you are going to get the values of A and B. Once you get the values of A and B, then you can apply once again the Lami's equation at the outer radius. So if the pressure is given, you have to take that value, otherwise it is 0. And X value, you have to take outer radius value, which is R0. Solve that, so you will get R0 value. Then R0 minus Ri gives the value of the thickness of the cylinder. So this is what I wanted to explain you. So two types of important types of problems in thick cylinder. One, sketch of radial pressure and hoop stress across the thickness. Another one, finding the thickness of the cylinder given the maximum stress value. So when they ask you to sketch, so it is left to you to have the intervals. So suppose if your RA value is 100, RO value is 200, you can choose the intervals yourself. So some 2-3 values you can find out in between. Then you can plot the points and join them by a smooth parabola. So that will be the parabolic variation because x square term is there. If 100, 200, 100 is the internal diameter, 200 is the external diameter, then what you can do is one value at 100, then 125, 175, 200. Like that you can take. So that interval you can decide yourself. Otherwise, in the exam, if they give the intervals at 20 mm interval, 30 mm interval, like that, if they ask, then you can take those values. For example, internal radius is, let us take internal radius as 150 mm, external radius as 200 mm. So 150 and 200. Then thickness becomes 50 mm. So you can put the values 150, 160, 170, 180, 190, 200, like that. Okay. So if they give those values, at those values you find out. Otherwise, that x value you can assume yourself. Starting value will be 150, ending value will be 200, like that. Okay. So once you know the inner radius and the outer radius, so that x values, minimum, maximum, will be knowing. That range you can decide into equal intervals, and you can find out that. So this is about what this is what I wanted to explain you today. Now, in module 2, we have covered principal stresses and strains and their planes, principal planes, maximum shear stress planes and their values, and how to find the tangential and normal stresses are in inclined plane. So those things we have covered along with the derivations. Then numericals also, problems also we have done. And next I cover thick cylinders. So both derivations as well as problems. Now still some more is left. That is graphical method of finding the major and minor principal stresses, which I will discuss later. That is called as Mohr circle method. Then some 2 theories of failure I have to explain. That is only theory. So that also I will take up later. So in the next class, I will be starting module 3. Very, 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 very important module 3, because bending moment and shear force. That is the basics for your structural analysis. So whatever you study in strength of materials, that is this is for structural analysis and design subjects in future. So you should be very careful in learning about bending moment and shear force, because that is very, very important in the case of design of beams, columns, slabs in RCC, steel, PSC, everything. So bending moment and shear force, is the very, very important chapter, module 3, which I will be starting tomorrow. Don't miss the class. If you miss the class tomorrow morning, you won't understand anything in future. So very, very important. So tomorrow morning, first hour I will be taking fluid mechanics class with the same link. You can join that class. And I want to know whether you have any other class tomorrow free. BMC class is there tomorrow for you? Wednesday? BMC class is there?
No, sir.
Wednesday you don't have BMC class.
Tomorrow we don't have.
Let me see. If any class is free tomorrow, first hour I will just inform you. I will check the timetable. Because some staff they are on leave. If I can get more class, because I have to do many things. So, but whatever I do, you have to practice. All the notes which I am explaining here, I have already sent you a mail as well as to WhatsApp group. Please download it, save it, and put it in a folder. Chapter wise, you put it in a folder, module wise. Then only you will understand. One book I have sent, R.K. Bansal, very good book. Lot of problems he has done in that. So you can go through that also. Only notations slightly it may differ, but you don't confuse with the notations. Whatever notations I follow, so those notations you can use. In some books they use P for the stress. In some books they use F. So that's all. So like that, they will use different notations, but concept-wise everything is same. R.K. Bansal book I have, which thin cylinder is also there. Actually, thin cylinder I had explained from that book only. If you remember, thin cylinder I had explained from R.K. Bansal book only. Okay, but thick cylinder
Yes.
I explained from a different book. This I am finding easy. That's why I took this one. Yes, yes, please. Any doubt is there?
No, sir.
Somebody was talking. What is that? Any doubt? Once you start working, then only you'll get doubts. If you don't work, there is no doubt. Okay. So two things can happen. If you have understood everything, there will not be any doubt. If you have not at all understood anything, then also there will be a lot of doubt. Then also you will not be having any doubt. So because you have not studied, there is no doubt. If you have understood everything, then also there is no doubt. So, but be careful. So you have to work. Unless you work, very difficult. So you can refer the problems which I have sent in that R.K. Bansal book also. Thick cylinder, you take the problems and solve, because answers are there. Answers are given in textbook. In the exercise problems also, answers are given in brackets. So you have to check the answers, because I cannot go on explaining all the problems. It's a very vast subject, and since you are not coming to college now immediately, so once you start coming to college, then we will how we can manage. So these portions, thin cylinder and thick cylinder, will be there for the next test. I'm going to include this in the next test. So two concepts I have not covered in module 2. One is Mohr circle, another one is failure theory. So those two things I will explain after I complete module 3. So module 3, bending moment and shear force. So please go through how you can find out moments and all. So how to calculate the moment you have learned in your engineering mechanics. Okay, that clockwise moment, anti-clockwise moment. So all those things, how to calculate the moments, equilibrium equations, all those things you have learned in your engineering mechanics. So non-concurrent force system, you know how to find the beam reactions. So you have to just go through that. So because I cannot go on explaining how to find beam reactions, which you have studied in your engineering mechanics. So that how to find beam reactions using equilibrium equations, that is very important for tomorrow's class. Bending moment and shear force. Please go through that mechanics support reactions. So three equilibrium equations are there. One is sigma fx0, another is sigma f0, fy0, third one is sigma m0. So sigma fx0, in most of the cases, it will not be there. Mainly in the case of beams, we are not using sigma fx 0. Only in hinged beams we are going to use it. Okay, fixed and hinged. Whereas sigma fy 0, sum of all the vertical forces including reactions should be equal to 0. That is sigma fy 0, and sigma m 0. Sigma m 0 is the algebraic sum of the moments of all the forces including reactions taken about any point should be equal to 0. So these three are called as the equilibrium equations. So once a structure is in equilibrium, so all these three conditions should be satisfied. This is for non-concurrent forces, when the lines of action of the forces are not meeting at a common point, just like forces acting on a beam. Whereas in the case of concurrent forces, which you have studied in your trusses method of joints, you have only two equilibrium equations, sigma fx0 and sigma fy0. Moment equation will not come there. Only it will come in the case of beams, sigma fx0, sigma fy0, sigma m0. So using those three equilibrium equations, how to evaluate the reactions on the beam subjected to concentrated load, UDL as well as UVL. UVL means triangular load, and also couple. See, there are four types of loads acting on a beam: concentrated load, UDL, uniformly distributed load, then uniformly varying load, and then you can have trapezoidal load also. Trapezoidal load can be divided into two types of loads, UDL and UVL. Then you have a couple or a moment acting on a beam. So these four types of loads, how they act on the beam, how to find the reactions. Mainly we are dealing with simply supported beam and cantilever beam. So bending moment diagram and shear force, bending moment and shear force, module 3, finding the bending moment and shear force in simply supported beams and cantilever beams subjected to these four types of forces, loads: concentrated load, UDL, UVL, trapezoidal load, and couple or a moment. So I want you to study those equilibrium equations as well as how to find support reactions. If you have any material of engineering mechanics with you last year, first semester or second semester, in whatever semester you have studied. In which semester you studied engineering mechanics, civil students? First semester or second semester? In which semester you have studied? Nobody is answering. You have not studied? You have not studied engineering mechanics. Which semester you studied? First semester or second semester?
First semester, sir.
First semester. Okay.
In first semester, we had engineering mechanics.
Yeah, second, I think. You studied in second semester. But you did not write the exam, is it not? You did not write the examination. Correct. So there, support reaction chapter is there, the equilibrium condition, support reaction, non-concurrent force system. So that you need for this module 3. That's what I told. So you see, all these subjects, they are interrelated. Mechanics, strength of material, structure analysis 1, structure analysis 2, RCC design, steel design, PSC design, bridge design. So they are all interrelated. So you should not forget the fundamentals starting from mechanics. Okay, so you just go through that. Tomorrow morning, first hour, I am taking, and if there is any other class free, I will let you know. So if any other class is free, I will follow. Anyway, my regular class is not there tomorrow. I know that, but anyway, portions have to be covered. I will take first hour, that is Chandragowda sir's class, FM class. You can join with the same link, and afterwards, if there is any other class free, I will inform you and I will take. Okay. Let me take the attendance. So go through whatever I have done today. Don't forget, finish up the studies on the same day. Otherwise, you will be getting lot of doubts. If you don't study today, you'll get lot of doubts. Make a notes of your own. You have to write this sketch, write the equations, solve one or two problems, solve the derivations. That's what you have to do. Otherwise, if time passes away, then we cannot help. We don't know when we will be coming to college. I don't know. University has to decide that. 1828. Tejas. Tejas. $19,001.
Present, sir.
00.
Yes, sir.
005. Darshan.
Present, sir.
006. Divyashri.
Present, sir.
7. Jahnavi.
Present, sir.
9. Nishant. Nishant. 10. Padma.
Present, sir.
11. Preeti.
Present, sir.
12. Rahul.
Present, sir.
13. Medhesh.
Present, sir.
15. Muzaffar.
Yes, sir.
16. Sri Lakshmi.
Yes, sir.
17. Shreyas.
Present, sir.
18. Shreyas.
Present, sir.
19. Shweta. Shweta.
ಸರ್
21.
ಪ್ರೆಸೆಂಟ್ ಇದ್ದಾಳೆ ಸರ್ ಮಾತಾಡಕ್ ಆಗ್ತಿಲ್ಲ
ಆಯ್ತು.
ಸರ್ ನಿಶಾಂತ್
21. ಸೂರ್ಯ.
Yes, sir.
ಆಯ್ತು ಕೊಟ್ಟಿದ್ದೀನಿ ಇಲ್ಲಿ ಸ್ಕ್ರೀನ್ ಮೇಲೆ ಇದೆ ನಂಬರ್ ಇದೆ ಇಲ್ಲಿ.
ಮೈಕ್ ವರ್ಕ್ ಆಗ್ತಿಲ್ಲ ಅಂತ
ಯಾರ ಆಯ್ತಾ? And be prepared.
Yes, sir. Yes, sir.